Okay, so again, you should have hopefully at this point taken this table. You should have went through this and learned these functional groups, because these are the functional groups you're going to have to use in this chapter and the rest of the chapters to understand the compounds we're talking about. Okay? And so, for example, some of the examples of this are thiols. Notice that they look like alcohols, but they have a sulfur in. Okay? Can everybody understand the R right here, what that means? So R here means the rest of the molecule or residue. Okay? It's the rest of the thing we don't care about. This part here that's highlighted in pink here is actually the functional group. So when I refer to thiol, all I'm talking about is this single bond to an S and then a hydrogen off that sulfur. Okay? This right here would actually be a sulfide or a thioether. This right here would be a disulfide. Anybody ever heard of a disulfide linkage? This is what gives you your hair curliness, in case you're wondering, and actually holds together a bunch of your proteins. This right here is the phosphate, as in like the phosphate backbone on DNA. And this is right here is actually the triphosphate for ATP. Right there. This is ATP right here. This one right here, this is the amine. So this is a primary amine. See, it has one R group on it. That's what makes it a primary amine. The one stands for one R group. The secondary amine has two R groups on that nitrogen there. And a tertiary amine has three R groups around that nitrogen there. Quaternary would have four R groups around it. This right here, this is an acetyl. What you'll see here is it is a double bonded oxygen here, and then it has a carbon, a CH3 here. Okay. This is actually really common in different biological molecules. You'll actually see it as acyl, is typically how they rename it. They just change the spelling. It's an acetyl group. This right here, it's a specific acetyl group. This right here is the aldehyde. One of the ways you can help yourself remember this is the aldehyde and ketone. The difference between those is the ketone has R groups on both sides. It has carbons coming out on both sides. The aldehyde is hiding a hydrogen there. Okay? And so it has a hydrogen on one side instead of two carbons on both sides. These are both referred to as carbonyls, meaning it's a carbon-oxygen double bond there. All right, can everybody see that okay? Carbon-oxygen double bond. We have one carbon on one side and a hydrogen on the other. It's an aldehyde. We have two carbons on both sides. We have a ketone. Okay, so this right here is carboxylic acid. Has any of you ever heard of an amino acid? All right, this is the acid part of an amino acid. Okay, that's carboxylic acid. Also vinegar. Vinegar is a carboxylic acid. And so this has a COOH right there. This right here is carboxylate. Notice the 8 part, as in it has a negative charge and we've lost a hydrogen. Okay? So here you'll see it has a negative charge and we've lost that hydrogen right there. Okay. By the way, the amino acids, this is an amino acid right here. Notice the hydrogen lost? That's what makes it an acid. Yeah. If it can lose an H+, that's one of the definitions for an acid. So this is actually going right here. This is the acid. This loses the H+, and it becomes a base here. And we'll go into a bit more depth later. We're just building up towards there. Okay. This is an amino acid, by the way. And look at the amine for amino, right? And the carboxylic acid portion right here for the acid. So that's what amino acid is. It has the side chain, which makes it the different types of amino acids that you might run into later. This is an ester right here. You'll notice it has a carbonyl, carbon-oxygen double bond, and then it's connected to an oxygen, which then in this case is connected to another chain of some sort. Okay? And so this is actually the linkage you find in things like the triglyceride, which is like the fats you get if you eat an animal fat or most oils and stuff. Okay? So this is actually the fats that you would be. Right? This right here is an amide. Everybody's heard of proteins, right? This is the bonds that hold together proteins. Okay? So these are called amide linkages when they're holding together proteins. And that's the amide right there. It has carbon-oxygen double bond and then nitrogen single bonded to that. And it has another chain that comes off of there. Okay, so let's talk about unsaturated. Everybody's heard of unsaturated fats? Okay, saturated versus unsaturated fats. Fantastic. All right, so unsaturated hydrocarbons are going to be things like alkenes. They're going to be carbon-carbon double bonds. That's going to be what makes them unsaturated. And so notice the alkene, we actually saw an example of one of these, didn't we? That was that octene, right? That we'd been looking at before. And so again, the alkenes, these are unsaturated because they have one bond between two carbon atoms that's extra, meaning they have less hydrogens around those carbons. Okay? The double bond is going to be shorter and stronger than a single bond. The alkene is going to react in an addition reaction. The second bond of the double bond will be broken, and the carbon atoms remain joining together by single bonds. And so alkenes that are more reactive than alkanes typically. And they can do a whole series of reactions. Has anybody ever heard of hydrogenation? As in like hydrogenated oil or peanut butter? So, anybody know how you make peanut butter? You take... So what you actually do is you take peanut oil, and peanut oil is an unsaturated hydrocarbon. It's a liquid at room temperature. You undergo hydrogenation, and it makes it into a saturated hydrocarbon. And that actually ends up being a solid at room temperature, but melts just a little bit above at the temperature of your mouth, essentially. Which is why you have that sort of like liquidy feeling of peanut butter in your mouth. Okay? Then so that actually is the difference between saturated hydrocarbons and unsaturated. Peanut butter. Again, the peanut oil is unsaturated. The peanut butter is the saturated. And if you want, you can take the nuts and grind them up and mix them. Yeah. That's chunky peanut butter. So unsaturated hydrocarbons, these are going to be alkenes. Alkenes are also found in terpenes. These compounds contain at least one hydrocarbon, at least one carbon-carbon double bond, as many as 5 carbons, some multiple of 5 carbons, excuse me. Okay, so again, this is a double bond, and this is an example of terpenes right here. So some of these common terpenes are going to be beta-carotene. This is going to give the like orange and red colors that you see, like a carrot. Orange color is the beta-carotene. Okay. Note that these different carotenes can actually have a whole host of different colors. That's why you can get like orange, but you can get purple carrot. Okay. B-limonene and alpha-penene. Cholesterol, testosterone, estrogen, these are all synthesized from terpenes as well. And so the terpenes are what actually make those. Okay. So the compounds that contain one or more carbon-carbon triple bond are, this is an alkyne. And the alkynes are again going to be unsaturated because they have less hydrogens than they could possibly have. Okay. The triple bond is going to be shorter and stronger than the alkene's double bond. Your alkynes are going to be even more reactive than the alkenes. Now, because they're so reactive, you typically do not see alkynes in nature. They're actually pretty rare. You see alkenes quite a bit, actually. And that's why you can find unsaturated fats all over the place, even if it's organic food that actually is organic. And if you just look around in nature, alkynes are pretty rare. And so this is actually an example of an alkyne. It's a toxin on this frog that builds up on this frog. And it's one of those toxins that is lethal if you don't have treatment readily available. Yeah. Okay, so let's talk about aromatics. Aromatics has nothing to do with smell. Okay, that was actually a misconception when they were named. And so they named them aromatics, but it made every other person that ever had to learn this confused. Okay, so no, aromatics has nothing to do with smell. It doesn't smell aromatic. Nothing to do with that. Okay. Okay. Aromatics are going to be like this. Benzene is the classical example of an aromatic structure. It's a cyclic structure that's similar to benzene. When it's part of a larger molecule, you'll call that phenyl as the substituent. Okay. So if you attach this benzene to something, if you had a carbon chain right where my red dot is, that would be a phenyl. All right. So when we look at this benzene ring, all the distances between those bonds, they're all going to be the same distance. Okay. I know that it seems like you have alternating double and single bonds, but that's because of the way we write these. We have limitations on how we can write them. Okay. In reality, this benzene ring is equal length for all these bonds, and each of those bonds is more like a 1.5 bond, rather than being single, double, single, double. Okay? Does that make sense so far? So again, because of how we have to write these, we only have a symbol for single, we only have a symbol for double, right? We write this as being alternating double, single, double, single, double, single, right? But in reality, it is not like that. What it actually is like is all these bonds are the same type of bond around here. Okay? Has anybody ever heard of resonance structures? No? Okay. I get to introduce them to you then. So, benzene resists reactions that would break these double bonds. Benzene is incredibly stable. And if you look around in the pharmaceuticals around you, you'll actually see this ring motif that either looks like this or has like a same sort of ring motif but with a little circle in it all over around you. Okay, you've for sure seen it on some bottle somewhere at a pharmacy, right? And that's actually a benzene ring because it's incredibly relevant in like chemistry and pharmaceuticals. Very, very common structure. Okay, so what we need to do to write out the benzene ring is we need to do something called a resonance hybrid. Okay? Because we have limitations on how we can write these things out using our double and single bonds, what we do is we write out the alternating single and double bonds. We then put a double-sided arrow, see the double-sided arrow? Okay. This double-sided arrow means we're making a resonance structure. Okay? We're writing two structures that in reality are one. We're encompassing the actual structure by writing out these two things that in reality represent half of that structure each. Okay? Is that making a bit more sense? Kind of like when you have to write out motion, you do it in several images and then flip through the book, right? We're doing it right here. Okay, so notice what we do is we alternate these double bonds. Can everybody see it okay? So these same carbons here are a double bond here. They're a single bond right there. And what we're trying to represent that in reality, these are like 1.5 bonds. They're a hybrid between a single and double bond. Okay. This is another way of representing that same information because benzene is so common and you see it so often. Chemists have made their own terminology to just represent the benzene. And so they make the benzene ring, and then they put a circle to represent this whole thing as one joined structure. Okay? Now, an interesting thing about this is that it actually does have a joined orbital with electrons in it up here. So this right here literally is a little circuit of electrons above and below the ring. Electrons just freely move in that. Okay? So benzene actually literally is like a little circuit above it. Kind of like some sort of large hadron collider in a molecule. Yeah, it's kind of fun and interesting. Little ring. It has really interesting chemistry, very, very strange stuff. Aromatic compounds that contain 2 or more benzene rings are called polycyclic aromatic compounds. That's PAH. The phenanthrene and benzopyrene are going to be 2 of those. These are actually found in tobacco smoke, and that's these right here. So some of these have been shown to be cancer-causing or carcinogenic. Aromatic compounds also are components of many plastics because they make the very stable plastic. So you can make incredibly stable plastics that will last a long time. Whether that's a good or bad thing, I'll leave you to decide. But anyways, that's become a bit of an issue lately. But usually things lasting a long time is a good thing. Okay. Anyways, you guys ever heard of Forever Chemicals now? It's been in the news a lot lately. I will say that there's been some studies recently modeling out if those had been bioavailable, if they had broken down, and at the levels we made them and dumped them in places, if they had been bioavailable and actually broke down, they would have destroyed those environments completely. Because we've dumped a lot of those. So whether they're forever chemicals and that's causing a problem to the buildup versus bioavailable and would have been able to break down, that's an interesting conundrum. But either way, we have problems we have to deal with. Okay, so the pharmaceuticals, these are going to be organic compounds. They're going to be an open package. Whenever you open the package of a prescription medicine, what you're going to see is you're going to see an insert that's going to include a description and a chemical structure. And so, for example, this is morphine right here, oxycodone. What did I say? Oh, okay.
So it's like ingredient.
Yeah, I have not had my water. Okay, so the lipids, these are going to be hydrocarbons. They're fatty acids. These are going to belong to the biomolecules that are called lipids. Fats with 1 double bond are going to be called monounsaturated. If you have 2 double bonds, you typically are just going to go straight to polyunsaturated because we kind of just give up counting really fast. Okay? So if you have 2 or more double bonds, typically you're just going to go straight to polyunsaturated. Technically, you could call them diunsaturated, that sort of thing, but nobody would actually know what you're talking about because they just don't do it. The saturated fatty acids is going to be long, straight chains. They're alkyne-like compounds. They do not normally contain double bonds because then they would be unsaturated fatty acids. They will contain, however, a carboxylic acid group at one end. And this is, in fact, why they're called fatty acids. So, notice the fatty as in fats, right? And they have an acid at one end, so they're fatty acids. Okay. Now, biologically, the important fatty acids are going to be compounds that contain 12 to 22 carbon atoms. Shorter, we do not typically call them fatty acids. Longer, they are going to not be biologically relevant anymore because they're going to be so long, they'd be essentially sludge in your blood. Okay? You would actually break most of those down. Now, the most naturally occurring fatty acids are going to have even numbers of carbon atoms. This is actually due to an important cycle in your body. So your biological reactions you do. So we have a system that works on even numbers of carbon. If you have an odd number of carbon, you actually have to go through an entirely another pathway to fix that. And so, by far and away, even numbers of carbon is the most common. Now, this right here is some of the more common fatty acids. Here we have lauric acid, that's 12 carbons, and that's the coconut oils right there. Myristic acid, that's nutmeg. Palmitic acid, palm oil. Stearic acid, this is your typical animal fat. So if you were to take your animal fat, have the fatty acid from that, that's that one there. That's the most common. This one's right here is actually peanut oil. Ooh, so good. Okay. You need to really concentrate on the functional groups. That's the one you really need to concentrate on. This stuff would be, if I give you a question, it would be like a reading question, and I would only give you like one or two of those on any given exam. Okay. This is behenic acid, which is canola oil. So let's talk about some fatty acids in our diets. Now, fats are incredibly important in a balanced diet. Am I still blinking in and out all the time? I'm going to have to go back up to lecturing up there. Okay. Now, the fats are going to be incredibly important for our balanced diet. They're incredibly important for us to continue living. They have roles as insulators, protective coatings for internal organs, nerve fiber coatings. They are our cell membranes. They make our various different lipids, which are such important things as like cholesterol, which is part of membranes, but also our signaling molecules. The most powerful ones, i.e. steroids, are typically made, are lipids. They're all lipids. That's what they're made from. Now, the Food and Drug Administration, FDA, recommends that a maximum of 30% of the calories in a normal diet comes from fatty acid-containing compounds. It also recommends the majority of the fat intake from the foods contain mono and polyunsaturated fatty acids. I'm going to be honest, don't take your nutritional advice from this book. Okay? Like, it's a good baseline of understanding nutrition, but it is not... First off, it's somewhat old book, right? Do you guys know the food pyramid? Do they still teach that? Thank God. Thank God. You had me really worried for a second. Okay, so having said that, the government has a very long and storied history of manipulating and giving really, really bad nutritional advice for the last 70 years. So they created the food pyramid. Does anybody know what the bottom of the food pyramid is? This is the second one. That would have made sense. That would have been smart. Yes. Yes. No, you were right. It should have been fruits and veggies on the bottom of the pyramid. That would have been smart. No, it was carbs. Grains. Do you know how many carbs you actually need in your diet? Yeah, you actually don't have to eat any carbs technically. It would be a really, really difficult diet to maintain. But yeah, you can go with completely zero carb diet. Don't actually do that unless you have a doctor monitoring you, by the way. It's actually kind of difficult to do. Okay? Correctly, not hurt yourself. So not as much about the physical activity, it's more about things like your brain and like immediate energy. Yeah. And if you have certain conditions, it can cause those to trigger and you can die. But other conditions actually can be controlled. If you go on a zero carb diet, you can actually greatly reduce the effects of epilepsy and several other things. So it's, anyways, it's an interesting topic, but yeah. Okay, so how about let's say are we getting better at this? Is the government getting better at nutritional advice? So let's look at, actually only 2 years ago, under the Biden administration, they did a nice website, And it was supposed to give you, like, if you typed in, it would tell you a nutritional score. And that was how healthy that thing is. Okay, so let's try it. Let's say we typed in Lucky Charms. What sort of score do you think that gave you? 60 to 70. So out of 100, Lucky Charms was rated a 60 to 70 for nutrition. What do you think an egg gave you? A boiled egg. Yeah. It kind of changed over the years during it, but yeah, basically like 28. So nutritional advice 2 years ago: eat Lucky Charms, don't eat eggs. So again, like if you actually want nutritional advice, talk to a nutritionist, and take it with a pinch of salt if they try to give you like a very extreme opinion. But usually they're going to be better than a government or. Mm-hmm. 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 Yes. Yeah, if you have somebody that's actually seeing how it feeds back, you can do pretty well on your nutritional guidelines. Especially if they do, so they do a metabolite screening. That's how all the billionaires do their training and diets and stuff. But it's not that expensive actually. So, and that does incredibly well. Anyways, so this right here is some different families of organic compound functional groups, and you can see here, like if you were to buy canola oil, you'd see that there's mostly it's going to be monounsaturated fatty acids. There's going to be a bit of polyunsaturated in there, and there's going to be a bit of saturated, very little. Okay. This is why canola oil was said to be very good for you a few years back. It is not. Anyways, that's why people had said that for a while. Funny enough, again, coconut oil, like another thing that had been a fad that is good for you. And it's full of saturated fatty acids that are very medium length chains. Honestly speaking, you need a balance of these fatty acids in your diet. You do. And you need very specific fatty acids in your diet. Okay? Talk to nutritionists, though, because this is a field that is not particularly well studied yet. Right? Because, the things you'd have to do to really study it well, you're not allowed to do to people. And there are getting data now because all these rich billionaires are going crazy on trying to live forever and are doing crazy stuff to themselves with scientific teams to watch them. So, this is a field that in 40 years is probably going to be really good, but right now is not so great. So the nomenclature for your simple alkanes. Now, alkanes do not have to have all their carbon atoms connected in a single continuous chain. There can be something called a branch chain on an alkane. Think of it a bit like a tree, right? We can have the root, the main trunk, right? And then off of there, we can have branches coming, right? And so if you were to look at the branch, would you go, hey, that's the tree? No, you'd go, it's a branch, right? It's not the trunk. Okay, and so you have to be very careful when you're naming these. Now, the nomenclature rules are established by an organization. It's called the International Union of Pure and Applied Chemistry, IUPAC. They're the ones that provided the unique naming for organic compounds. They ensure every organic compound has just one correct systematic name. They are people. They do make mistakes, but it's been worked out pretty well by now. Okay, except for some of the things that are really hard to say. The names for organic compounds are going to, again, have three basic parts. It's going to be the parent or root name, okay? And that's the part where you count the longest continuous chain, and that's what we were using, for example, the octane, those sort of things. We're going to have the prefixes, which are going to list your various different substituents that you substitute hydrogens for. And then we're going to have the suffixes, which are going to be our family names. There's going to be important functional groups on that chain that we want to name that chain based on. Those are the things like the enes, the ines that we had been discussing, and the alcohol. that we had been discussing, OL. So step 1 is going to be find the longest continuous chain of carbon atoms. This is going to be your root or parent chain. Make sure you count from the each end to every other end. Make sure you find your longest chain. You can kind of use your logic to figure it out, but do you have to start like on the left, let's say? No. Notice that is nowhere in there, right? You could start at the top, you could end on the right. Okay? It doesn't matter where you start and stop. You start one side of the chain, you go all the way through until the end. Okay? Let's say we had a chain, right? This is a chain. And we had something coming off it like so. Okay? Can I go 1, 2, 3, 4? Is that continuous? It didn't look continuous, did it? No, it has to be continuous. It has to be one continuous chain. Okay? All right. So step 2, identify the groups bonded to the main chain, but not including the main chain. These groups that are bonded to the main chain, these are going to be substituents. They're substituting spots where hydrogen would normally be. Okay? They can be named, if they're branched alkanes, as alkyl groups. Notice again the alkyl, that's how you name them. So if you had a methane that was a branch, it would be methyl. Okay. You're going to change their namings from the normal ane naming to YL. Okay, so if I had a 2-carbon branch, what would I call that? So 2 carbons would normally be called what? Ethane, right? If it's a branch, it's going to be called ethyl. Okay? If I have a propane, it's a branch instead, it's going to be propyl. You'll actually notice, you've said this before. Anybody remember isopropyl alcohol? No? Like rubbing alcohol? So isopropyl alcohol is using this name. Okay, so number the carbons of the parent chain starting at the end near to the substituent, so you get the lowest possible substituent numbers. Number 4 is going to be assign a number to each substituent based on its location, listing the substituents in alphabetical order at the beginning of the name. Separate the numbers and words in the name by a dash. So if you have a number adjoined to a word, letters, you're going to put a dash in between. Okay? If you have a word going to a number, you're going to put a dash. Let's go ahead and look at this for the different numbers of substituents. So if more than one of the same type of substituent is present in the compound, we're going to indicate this with our Greek prefixes, which is di, tri, and tetra for those first ones. We're going to ignore the prefixes when we alphabetize to get the order of our name. Like any language, this is going to be truly learned by using it. Okay? So this right here is our substituents. So right here we have a chain, the parent chain here, or the root chain. And then this would be a branch coming off it, and this would be called methyl. If we have 2 carbons in a branch, that's ethyl, 3 carbons, propyl. Now the isopropyl that you may recognize from isopropyl alcohol is just a propyl where you're connected in the middle. Everybody see it okay? This creates a sort of V shape to it, like this, coming off your main chain. Okay? And that V shape is what's referred to as isopropyl. Okay, let's talk about haloalkanes. Now, halogens are going to be common substituents on alkane chains. These are going to be referred to as haloalkanes or alkyl halides. The substituent names of the halogens are going to be fluoro, chloro, bromo, iodo. So let's say we had an ethane with a chlorine on it. This would be chloroethane. If we had a bromine on it, it would be bromoethane. So the rules for naming are going to be the same as branch chain alkanes. The halogen is just going to be substituted up front and added on as a prefix. at the beginning of your name. Cycloalkanes. These are going to be round alkanes. So you're going to have a round chain that connects back in on itself. The ring is going to serve as the parent name as long as it has equal to or more carbons than any other substituent. You're going to identify the substituents. You're going to number the carbons in the ring. Carbon 1 will always have a substituent. You're going to assign numbers to the substituents. So on a ring bearing a single substituent, a 1 is going to be implied because that's where you're going to start. The ring should be numbered to give the lowest possible combination of numbers. Okay, we need to talk a bit about isomers. Now, I want to really quickly practice a problem. Okay. Give me the name for what's that? So the first thing we need to do is we count our parent name, right? So we count our number of carbons in that ring, right? So how many carbons are in that ring? 6, that is. So this would be a hexane if it's flat, single bond, right? If we have it in a ring shape like that, that would be cyclone. Perfect. And then we have something attached here, don't we? We have chlorine attached, don't we? And so that's going to be for our prefix. Okay. And that's chlorocyclohexane. That's the name. Now, in this case, we only have one of them. We don't actually have to indicate the number here because there's only one possible position it could be. 1. Okay. D for carbon. Automatic. Okay. Technically, this is not wrong. It's just you're using extra letters. Okay, let's go ahead and see if we have 2 of these. Okay, so what if we have something like that? Well, the parent's the same. Okay. This part, though, is a little different. We don't just have one of these. We have 2 now. And so what we're going to do is we're going to use for the number of chloros on there, the number of chlorines, we're going to say dot 2. Okay? If there had been 3, that would have been 4. Okay. You are probably never going to encounter more than 4, to be honest. If you do encounter that, you can look it up. Okay, and so we have 2, right? All right. So, well, we need to number on these 2 because there's more options, aren't there? We could have had a variety of leave this one now. That's a possibility. Okay, so for this one right here, we're going to number this to give us our lowest possible number. Okay, that would be 1 there. This one would be 2, 3, 4, 5. That will give our carbon number, our locant numbers. Okay, our locator. And so what we're going to do then is we're going to give the addresses we can find each of these chlorines. So it's going to be the first carbon. So first carbon, everybody see that? So we can find it. We go to the first carbon, we find our first constituent. We go to the second one, we can find the other. And now we've added our locant. We got that so far? You start seeing how that's applied. Okay. Now, please make sure you practice these right away because you will lose it just like anything. Okay. Very, very easy. Okay. Now, let's go ahead and name that one real quick. What would this one name? Just texting. Cyclo, right? Okay. And so all it changed is we needed to number this, right? So this would be 1 up here, 2, 3, 4, 6. And so it's off the first and 4. Okay. One more real quick, and then we'll keep moving on. All right. So how about if we did where are we starting it? Figure out the parent name, right? And so how many carbons is in your ring? Perfect. What can I count it? Not right. That's going to be a branch. Okay. And so the next thing I'm going to do is I have 4. That is what? For the parent. You have how many sheets? Not tetra. Okay. The easy way to remember this: butane. You have 4 sheets. Go on your face. Go on your butt. Right. Butane. Okay. Okay. And so we are going to say, like the lighter fluid. Okay, now, is this just butane, or do we need to put something else? And then what else do we have to put here? What's this group here? That's a branch, right? That's a branched alkane chain, okay? And we need to label that. Well, what would 1 carbon be? Methane, right? We're going to change the methane. And go. So this will be okay. So again, you need to practice that. All right. Now the next thing we're going to start up on is the organic compounds of the same number of carbon atoms. These can have carbons that will be connected in many different ways. You may have noticed I just drew something up there that was 5 carbons, right? And yet we didn't end up with a pentane. So the molecules with the same molecular formula but different connectivity arrangements of the atoms, these are going to be referred to as isomers. This name is actually taken from the Greek iso, meaning same, and meros, meaning part. So isomers are going to be different arrangements of these. Okay, we'll start up here next time. And I will end up moving chapter 5 and the ending chapter 4, post chapter 4. Could somebody send me an email to remind me though?
To move them?
Mhm.
To the dates?
Yes.